Today we'll just be looking at some of the introductory concepts in relation to hubs and a small section of PCs. We'll look at the collision issues that arise from a hub-based network, and then we'll have a quick look at the switch-based networks and logs as well. So having opened the application, we will go to File and New, and you can see that we get a new palette opening here. Also, at the top right-hand corner, we can now see, top left, that we have various options open to us. So in this case, as we let the mouse roll over it, the flag will pop up telling us what the icons are. So create, add a computer, add a hub, switch, router, so on and so forth. So we're going to start off with a very basic network. So we'll go with 2 PCs and we'll add a hub into the middle. Okay, and I'm going to label these properly, so especially when you're starting off, it's much better to have things labeled quite efficiently. It just makes it easier to keep track of who's sending what to whom. The way I do this, certainly initially, will be to give them a name that you'll remember. I tend to use various cartoon characters, so we'll stick with the classic Simpsons in this case, and we'll go with Homer for the first computer. I'm also going to specify the IP address and the subnet mask, just so that we can keep track of it quite easily. So 10.10.10. In this case, I'm going to go .1/8, and we'll have a look at that dotted decimal notation in more detail. I'm going to label the second PC. We'll stick with Marge. So Marge, and again 10.10.10.2. And if you remember from class, we said that all these IP addresses, these numbers, can be analogous to a postal system. They need to be absolutely unique, otherwise the data won't know where to go effectively. Especially if there's a clash, it just will crash the system on us. /8. We can move Marge up here as well. Let's use the cable connectors, and we'll connect. So ETH0 from the Homer PC is Ethernet, so it's the network card to LAN 1, which is fine. And we'll connect out. So LAN 2 to ETH0 on the Marge computer. That looks good too. Now, before we kind of send any packets of data shooting around the place, I'm going to do 2 things to make our life easier, just to keep track of what's happening. I'm going to set the description of the computer. So between the B tags, this is very basic HTML tagging language here. So where it says computer, I'm going to replace with Homer. So when we set the log up, it's going to pick up this name as opposed to just a generic computer. And generic computer is going to, it will keep it quite tricky to follow what's going on where. Okay, and we'll do the same with Marge. Set description and Marge. Now you might be wondering, where is that making a difference? But if I come back to Homer and right click and show log, so you can see over here the log, this log is now belonging to the Homer computer. Do the same to Marge, right click and show log. You can see this belongs to Marge. So excuse me. You can see now from the palette we have labeled this computer very clearly. We can see the IP address and the subnet mask very clearly. We've labeled Marge and the subnet mask and IP address, and we can see from the logs who's going to be doing what. So before we set up the IP address on the computers, you're better off to have the palette set up like this, so it's as transparent as possible as to what's going on where. The second you set the IP addresses up, communication is going to start. So as opposed to retrospectively trying to catch up with what's happened, you're better off to have it at this stage. So net cards, and the IP address we specified was 10.10.10.1. We're going to keep the default subnet mask. So in this case, for Class A, and the first octet goes from 0 to 126. So 10 is right bang in the middle of Class A address. The default subnet is always /8 for that. And what we mean is, so if there's 8 ones here, and 8 ones, and 8 ones, and 8 ones in each of these octets, 255 is where all the bits in that octet are ones. All the bits in this octet are zeros. All the bits in this octet are zeros. All the bits in this octet are zeros. So when the 8 ones here are all ones, we can also refer to that as /8. Click on apply and OK. The second we've done that, you can see, let's just pause this. The Homer PC is initiating communication. Okay, now if he had no IP address, which we'll look at in a later tutorial, we would need to get some type of DHCP request going to try and get an IP address. Not an issue here because we have given a fixed IP address to the computer. But now the computer is sending out a broadcast, an ARP broadcast, and it stands for Address Resolution Protocol. And what it's saying is, hey guys, the Homer PC is here, my IP address is 10.10.10.1. Most importantly, on the local LAN, my MAC address is, we can check what the MAC address is. So the MAC address is this address here, 01B7E986C5B5. Don't need to remember that in any shape or form. But if you remember from the theory in class, when we communicate on the local area network using hubs and switches, it's at the MAC address level. Our frames is what we're working at. It's only really when we're going between different networks and we need routers that IP addresses become absolutely critical. Not critical at this stage. So what Homer is doing is it's telling people, hey guys, this is my IP address, but this is the MAC address that's associated with it, because that's how you're going to be communicating with me at the local area network. And you can see the ARP request here. So 10.10.10.1 is Homer's address, and it's sending it back to itself. So in essence, it's broadcasting at every place in the network. And we know it's a broadcast. If you look here, the receiver, all F's in hexadecimal code. I know we didn't really cover hexadecimal code, we briefly mentioned it. It's to base 16, but all you need to know is that all F's equals all ones, and all ones is always a broadcast. So it's saying I'm sending from my address to every single PC or node that's on this network segment with this hub or the switch or whatever the case is. So okay, so Homer has sent out the two packets, or two frames in this case. So you can see it's going to be sent across to Marge, and Marge will receive both of these ARP requests. We just wait for them to come in, and you can see the ARP request has come in. Okay, so let's set Marge up. So 10.10.10.2 I think I said /8. So we'll just keep 255.0.0.0. Apply and OK. Straight away you can see that Marge is now looking to communicate out as well. So Marge is now sending out. So sent from Marge to back. She's effectively looping it back to herself. Again, an ARP request. She's sending out to anywhere in the network. How you doing? Marge here. My IP address. Most importantly, here's my MAC address associated with that. So that's the Address Resolution Protocol. Okay, so excuse me. If we were to send out a basic UDP datagram, User Datagram Protocol, click on Next. I'm going to go from Homer to Marge. It's to be received on Ethernet 0, that's fine. Now you can see here that there's loads of packets of UDP being sent out. So in this case, let's just have a look at any of them. So sent from 10.10.10.1, which is Homer. We have specified it's to go to Marge, 10.10.10.2. It's a UDP. If you remember again from the theory, this is a best effort delivery protocol. So I will send it out onto the network. I hope that the recipients receive it. If they don't, it's not been resent. We would very commonly use UDP for various requests. It could be a DNS request, but also for things like if we're in a voice call, if we're Skyping or something like that. So if you want to think of it like this, if we drop a packet of data in a real-time communication, we can't try and reinsert it at a later stage. Otherwise, the conversation would become meaningless. It just something that happened 5 seconds ago we could artificially try and reinsert it into the conversation. So UDP is a best effort delivery. TCP, on the other hand, is connection orientated, and what that means is that we enter into a handshake protocol. So I effectively, if it was Homer would say to Marge, hey, I'm sending this out to see if you receive it. And Marge will come back and say, hey, how you doing, Homer? I received your message, I acknowledge it. And Homer would acknowledge the acknowledgement and then send out the data. And Marge at the very end of it will acknowledge all the data that she received up to the last packet of data. And Homer will know if the last packet number is what he sent, and if it's not, he will resend whatever's missing. And that's the way that we ensure that TCP ensures that all packets are delivered correctly. TCP is a very heavy protocol. And by heavy, I mean that it takes a lot of overhead to manage it to make sure that things are working correctly, whereas UDP is much lighter. Okay, so back to our current scenario. So Homer is looking to send just some UDPs across to Marge, and the hub, as you can see, is going to send it out. We expect no communication back from Marge because, again, it's not that we don't care if she receives it, but if she doesn't receive it, we're still not doing anything about it. Okay, and you can see from Marge that she's received, so just have a look at any of these. So from Ethernet sender, this is Homer's PC, the receiver is Marge's PC, the MAC address. You can see the IP sender and receiver. TTL is a time to live, so it would facilitate maybe to stop loops that we can just kill the packet if it's going too long, and just the sender and receiver ports. Okay, so let's add in an extra PC into the mix just to see what happens. I'm going to call this one Bart for obvious reasons. Let's give Bart 10.10.10.3/8. We'll connect Bart up. Okay, to LAN 3 is fine. And right click and set description. So let's call this computer Bart again. And let's put the address in. Actually, sorry, before we put the address in, again, we should show the Bart computer's log so we can keep track of Bart sending out the ARP request. So netcards 10.10.10.3 and keep the same subnet mask, apply, okay. So straight away you can see that Bart has now sent out his two ARP requests. Now if you look up here up the top, you can see that it's been flooded out both ports of the hub, which is correct, and this would also happen on a switch at this stage because Bart is broadcasting to everyone on the network segment, hey, I'm Bart, I'm on this network now, here are my details and here's my MAC address. Okay, so we get Homer and Marge to receive. They're not going to respond. You can see that they've received the ARP request and they can map their own tables, will now map that IP address back to that MAC address. Okay, so if we do subsequently look for Bart to communicate with a TCP, so again, remember this is the connection orientated session, so we expect our little handshake protocol. We want Bart to communicate to Marge. Okay. Again, been flooded out both ports. So Marge is sending communication back. So let's just have a look at this. We'll see where Bart receives it. But again, now Homer is also receiving it. So, excuse me, if you can see this little red packet here. So in essence, all communication from Bart to Marge and vice versa is also going to be flooded out to Homer. Homer's PC will just ignore it. But in essence, it means that this line is always active with data that has nothing to do with Homer. So Homer, in turn, cannot communicate back to the network. We call this, if you wanted to draw a circle around this entire network in your head, this is its own collision domain, which means any device can collide with another device if a message has been sent. This is quite problematic on hub-based networks and is one of its main disadvantages. So the larger this network gets, actually in truth, the less efficient it becomes, because as multiple devices try and talk, they're going to collide, the packets are going to collide with each other, or the frames, and they're going to interfere with each other. Once this collision has happened, all the computers enter this random back-off timer, and then when the timer finishes on the first computer, it pops its head above the parapet, has a little listen to see if it's clear to send, and then ready to transmission, it will send back onto the network, presuming another collision doesn't happen. We call this protocol is called CSMA/CD. Carrier sense multiple access / collision detection. So carrier sense, let's determine the medium that we're on. Is it wired? Is it wireless? Multiple access, there can be multiple parties involved in this protocol. / collision detection. So in a case of wired networks, we can physically detect a collision happening. So as we're sending ones and zeros over the wires, this is done using voltage. So let's say Homer sent a frame, and Marge is also sent a frame, as has Bart, and they collide. So if there's 6 volts and 8 volts and 10 volts, when they touch each other, there will be a spike in voltage, and we can detect that, and straight away we know that there's been a collision, and we enter into this random back-off timer. So that's the CSMA/CD. If it was a wireless network, CSMA/CA, it's collision avoidance, which means on a wireless network we can't determine a collision in midair. We don't have the technology to do that. So we need to put much more overhead into managing wireless networks to make sure there are no collisions midair. Okay, so back again to the diagram at hand. Let's see what's happening here. So yes, as we can see, Marge sent the TCP response to Bart, and we can see here that Marge has acknowledged the initial handshake. So remember, Bart sends a sync message, okay, to Marge. Marge receives the original TCP sync. She acknowledges it. Bart acknowledges the acknowledgement, and then he's going to send out the full TCP communication. Close these up. We'll tidy these up a bit. And we can see Marge, if we have a look here. So Marge has just acknowledged this, the TCP acknowledgement, and now you can see Bart is sending out the actual communication. But look, again, as I said earlier, it's been flooded to Homer, even though Homer has nothing to do with this conversation. And you can see all the TCP has been sent out here. So if we have a look at any of these, Ethernet sender and receiver, IP sender and receiver, and the TCP. And you can see in this case no acknowledgement. This is just a stream of data. When the stream is finished, Marge will send back an acknowledgement for the last number she receives here, and this determines then this will determine to Bart what was the last package that was actually received by Marge. Okay, if you remember as well from our conversations, we call this process here encapsulation. So as the data was created, it was encapsulated into a TCP segment, into an IP packet, into an Ethernet frame, and sent onto the wire. As the other computer receives it, it decapsulates. It takes off the Ethernet header and trailer, has a look at the source and destination MAC address, the IP, it decapsulates that, has a look at the IP address, it decapsulates, so it strips off the header, has a look at the TCP details, it strips that off and gets up to the data. The data could be a HTTP request, a web browser request, or something to that effect. So again, that's just encapsulation and decapsulation. Okay, so we can see that Marge is going to receive all this data. So Marge has received it. You can see Homer also received it, but Homer just does nothing with it. Now Marge is acknowledging the last packet that was sent. Okay, if we have a look at that. Okay, before we just pause that. So TCP, so Marge is acknowledging packet 1747, and that would have been the last ISN that Bart had previously sent. So Bart now knows that communication was successful, and he's going to send out another stream of data. Okay, so this is the basic mechanism as to how the actual hub will work. You can see the disadvantage quite quickly as the network increases, that the speed of a hub-based network is going to decrease. The hub, really all the hub does, it's a very unintelligent piece of equipment. It will take the message that it is received, let's say from Homer on port 1, it will amplify it, it will clean up whatever interference is on the line, it will amplify it, and it retransmits it out every single port that is connected to it, bar for the one it received the communication on. So these guys tend to have to half listen and half transmit, so it's a half duplex mode is what we're looking at. Okay, so I'm going to stop this video now, and we'll continue on the next video with a switch variant of the same network. Thank you.